Hello everyone, in this video we're going to learn how to determine if the series is convergence or divergence using the integral test theorem. Alright, so the integral test theorem says if the function f is positive, continuous, and decreasing for all real value s greater than or equal to 1, and a sub n equals f of n, then the sequence and the improper integral either both converge or both diverge. Alright, so we take a look at the first one right here. Okay, so we let f of s equals 1 over s squared plus 1. Alright, this guy right here. Alright, for s greater than or equal to 1, because n goes from 1 to infinity. Okay, so first we need to check if this function is positive or not. Alright, so we check the first one. Positive. Alright, for s greater than or equal to 1, we substitute over here. We see that the function always positive, always above the x-axis. Alright, so this is yes. Now, continuous. Alright, we look at this one because s greater than or equal to 1, so the bottom always greater than or equal to 2. Alright, so it's the bottom, there is no holes right here, so the bottom cannot be equal to 0. Alright, so there is no hole, the function always continuous. And if we have to use the decimal to check, yes, we can do it. So y equals 1 over s squared plus 1. We see that the function always continuous, right? So this one, yes. Now, we need to check the third one if the function is decreasing. Alright, so in order to check if the function is decreasing, we need to take derivative of this function. Alright, so basically differentiate this one. So we have f prime of s equals. Now we have u over v. Alright, we need to differentiate this one, so it turns out to be u prime times v minus v prime times u over v squared. Alright, 1 prime times s squared plus 1 minus s squared plus 1 prime times 1 over s squared plus 1 square. Alright, equals this guy 1, derivative of 1 is going to be 0, so this guy is 0. Derivative of this one, it turns out to be negative 2s, right? So it could be negative 2s over s squared plus 1 square. Now we look at the domain. The domain right here, s always greater than or equal to 1. So this guy is always less than 0. Alright? So because this guy less than 0, which means f of s is decreasing. Alright, so this one decreasing, yes. So because the function f satisfies 3 conditions right here. Alright, for s greater than or equal to 1, then we need to determine if this one converge or diverge. So we need to take the integral from 1 to infinity of this guy right here. 1 over s squared plus 1 ds. Alright, so this is improper intervals, we need to use the limit. So it can be limit when b approaches infinity of the interval from 1 to b 1 over s squared plus 1 ds. Alright, so it's gonna be limit when b approaches infinity. Antiderivative of this one should be tangent inverse of s. So it could be tangent inverse of s. Evaluated from 1 to b. Alright. So it's gonna be limit when b approaches infinity of tangent inverse of b minus tangent inverse of 1. Now you substitute b over here. So we have tangent inverse of infinity should be pi over 2. And this guy should be pi over 4. Alright, so pi over 2 minus pi over 4 should be pi over 4. So the interval from 1 to infinity of f of s ds converge. If this one converges, we have the series of 1 over n squared plus 1 when n goes from 1 to infinity converge. Alright, let's move on to the second one. Now, the first one right here converges. Converted to pi over 4. Okay. Now the second one. So we consider the function f of s equals s over s squared plus 1. Alright, we do the similar process. We need to check to see if the function f is positive, continuous, and decreasing. Alright, so first positive. Alright, don't forget the domain s greater than or equal to 1. Alright. So we substitute s greater than or equal to 1 over here. We see that the function always positive, right? If we use like 1.1 or something like that, look. So it's always positive. 2 is still positive. It cannot be negative, right? So this is yes. Now, continuous. Alright, this is absolutely continuous, right? Right, there is no hole because the bottom cannot be equal to 0, right? Or you can use decimal to check if the function is continuous. So I have right here, it's going to be s. See that the function always continuous, right? Alright. So this is yes. Now decreasing. In order to determine if the function decreasing, we need to differentiate the function. Alright, so I have f prime of s equals. Now we apply the same formula right here. Alright, so we have s prime times s squared plus 1 minus s squared plus 1 prime times s over s squared plus 1 altogether square. Alright, so it's gonna be s prime is gonna be 1, so the top should be s squared plus 1. This guy is gonna be negative 2s times s is gonna be negative 2s squared over s squared plus 1 altogether square. Alright, so we need to simplify. It turns out to be negative s squared plus 1 over s squared plus 1 altogether square. And don't forget the domain s greater than or equal to 1. Alright, so we need to determine if this guys right here less than 0 or greater than 0, right? So we start with the domain right here. Alright, so I have the domain is going to be s greater than or equal to 1. I'm going to square both sides, so it could be s squared always greater than or equal to 1. Alright, so I'm going to multiply both sides by negative 1, so it can be negative s squared less than or equal to negative 1, right? So I'm going to add 1 both sides, right? So it can be negative s squared plus 1 less than or equal to 0, alright? So I'm going to divide both sides by s squared plus 1 squared right here by a positive number, right? The bottom is a positive number, so it can be s squared plus 1 altogether square. Right, this one divided by this one is going to be 0. So the whole thing right here is always less than or equal to 0. So the function is decreasing. So this is yes. Alright, next step, we need to determine if, right, this one converge or diverge, right? So we have the integral from 1 to infinity of s over s squared plus 1 ds, right? So observe the bottom right here. If we differentiate the bottom, it's going to be 2s, right? So we look at the top right here, it's just only s. So I multiply the top and bottom by 2. So 2 right here, and I put 1/2 right here. So this one can be written as 1/2 limit integral from 1 to b when b approaches infinity of 2s over s squared plus 1 ds. Alright, this one turns out to be 1/2 limits when b approaches infinity of natural log of absolute value of s squared plus 1. Alright, so because s squared plus 1 always positive, so I don't need to use the absolute value side right here. So I can remove the absolute value side right here. I just put the parentheses right here. And evaluate this one from 1 to b. Alright, so it's gonna be 1/2 limit when b approaches infinity of natural log of b squared plus 1 minus natural log of 1 substitute over here is going to be 2. Alright. Now when b approaches infinity, this guy always goes to infinity. And this guy is too much smaller than this one. Alright, so the whole thing should be infinity. This means the integral from 1 to infinity f of s ds is divergent. If this one diverges, the series of n over n squared plus 1 when n goes from 1 to infinity is divergent. And it's good time to stop. Thank you for watching. I hope you enjoyed the video. Remember that if you failing to prepare, you're preparing to fail.
We rise like tall buildings as the chemicals they take us higher. The night's young and it's just begun as she puts her hand